Welcome to AI Paper Podcasts. We're the show that tries to pull out the key ideas from dense AI research papers. Today we're looking at a really interesting one that kind of shakes up how we think about generating high-quality images. Equilibrium matching, or EQM, by Runke and Wang and Yilun Du. Okay, so if you've only got a minute, here's the gist. For a while now, models like diffusion and flow matching, they've been stuck with these non-equilibrium dynamics. They always need to know the time or the noise level. EQM basically says, let's just scrap the time conditioning completely.
That's exactly it. And the way EQM does this is, well, it learns a single, unchanging equilibrium gradient. Think of it like an energy landscape, where the real data points are like stable valleys or local minima. So instead of needing time, generation just becomes an optimization problem, like rolling a ball downhill on this energy landscape.
Right, and that shift unlocks some really neat tricks for inference. They can pull in standard optimization tools like Nesterov accelerated gradient.
Yep, NAGD. And crucially, adaptive compute. So you can stop the process early if the image looks good enough, which saves a ton of processing.
And the headline result, pretty impressive.
Yeah, it really is. EQM hits an FID score of 1.90 on ImageNet 256 by 256. That beats other big models like SciT XL2 flow matching, which is at 2.06. It suggests, maybe this simpler, stable approach is the way forward.
Okay, let's really unpack this then. Before we get too excited about equilibrium, maybe talk a bit more about the problem itself. What's the actual pain point for researchers using these classic flow matching models with their non-equilibrium constraints?
Well, the main thing is rigidity and wasted computation. Flow matching, you have to define this path from data to noise, right? And the model, this topics TTT, it has to learn the exact speed and direction to reverse that path.
So the time step is absolutely essential because the velocity it needs when it's almost pure noise is totally different from when it's close to the final image.
Exactly. It's a dynamic target. The training objective for flow matching, YLFM, it's all about matching the model's predicted velocity, LX to Adeller, to the ground truth velocity, which is 6x epsilon. And since that target velocity keeps changing with time $2, you just can't get rid of $2. This locks you into a fixed integration process for sampling. You got to take all the steps, maybe hundreds or thousands, even if the image looked pretty good halfway through.
Right. And people have tried to just yank out the time conditioning before, haven't they? How did that go?
Oh, it was not good. Noise unconditional FM, they called it. The generation quality just completely fell off a cliff. It really seemed to confirm this idea that, okay, if you do want to remove time, the gradient field you learn must be compatible with equilibrium. It needs to describe a fixed landscape, not this constantly shifting path.
Got it. So EQM basically takes that hint. It changes the whole objective. Forget the moving target. Let's find one single stationary gradient field from an energy landscape. How does the training objective, level EQM, actually build this landscape? This feels like the core novelty here.
Yeah, this is where it gets really interesting. They borrow heavily from energy-based models, EBMs. So they define a corrupted sample, 6 gamma x plus 1 gamma epsilon. Standard stuff so far. But here's the key difference. The model, GATA, only sees that corrupted sample 6 gamma. It doesn't get the noise level gamma as input.
Ah, okay. So the model has to figure out the noise level implicitly without being explicitly told you're at time step T or noise level gamma.
Precisely. And the objective, GATA-XC, then tries to make the model's predicted gradient, XXC, match a target gradient. And that target is epsilon XC. Notice the direction, epsilon XC. It points from the noise towards the data. That's the direction you'd want to go to descend the energy landscape, right?
Right.
To get back to the clean image.
Okay, that makes sense. And this magnitude function you mentioned, there's a constraint that epsi-guess has to be 0. Why is that specific constraint so important for making the data point stable? Can you break that down a bit?
Sure. Think of the energy landscape again, maybe like a hilly terrain with valleys where the real images is supposed to be.
Mm-hmm.
If you're standing right at the bottom of a valley, which represents a perfect ground truth image, so gamma dollars, the ground should be flat. Right? The gradient, the force pushing you, should be 0. If d over dollars wasn't 0, the target gradient would still be non-zero, even when you're at the perfect image. The model would predict a non-zero gradient, and it would try to push the sample away from the valley floor.
Like standing at the bottom of a bowl, but the bowl itself is, actively tilted?
Exactly. That's a great analogy. By forcing 6 dollars, they ensure that when 6 gamma is a perfect data sample, the target gradient is 0. The model learns to output 0 gradient, and you get a stable stationary point, a place to rest. That's absolutely vital.
Okay. And they played around with different ways to define this Zima function, right? What did they find worked best in their experiments, their ablations?
Yeah, they tried a couple. A simple linear decay, like linear 1 gamma, worked okay, but the best results came from something they called truncated decay. With that one, the gradient magnitude gamma stays constant and strong when there's a lot of noise, up until gamma is, say, 0.8. Then, as you get closer to the data, as gamma goes from 0.8 to 1, it drops off linearly to 0.
So a strong push from far away, but then it eases off gently near the target.
Exactly. Get it in the right direction quickly, then refine carefully. They also found that scaling the whole objective with a gradient multiplier, lambda Focal of 4 specifically, gave another performance boost.
Okay, let's switch gears to inference, to actually generating images. Since EQM sets up this fixed energy landscape, sampling just becomes gradient descent, right? 6a plus 1 is basically 6km minus some step size times the gradient. What are the really big practical wins that this optimization approach gives you compared to the sort of fixed step-by-step integration in flow matching?
This is a really important point, yeah. The main advantage is you suddenly get access to like 100 years of research in optimization theory. Flow matching is kind of stuck with its specific integration method, but EQM, it's just minimizing a function, so you can use all sorts of established techniques.
And the first one they highlighted was Nesterov Accelerated Gradient, NAGD. Why would acceleration be particularly helpful here for generation?
Well, think about that energy landscape EQM creates. It's probably pretty complex, right? You might have these big flat areas, sort of plateaus, maybe near the data manifold, or maybe small bumps, little energy barriers to get over. Standard gradient descent can really slow down or even get stuck in those flat regions where the gradient is tiny. NAGD uses momentum. It kind of looks ahead based on the current gradient direction before it actually takes the step. This helps the sampling process build up speed, sort of glide across those flat basins faster, or power over small humps. It just converges quicker and often finds a better minimum.
So it's not just about speed, it's about navigating the landscape more effectively. And the results showed this worked. It got them that top 1.9Z FID score.
Absolutely. It's a nice validation. Treat generation-like optimization and standard optimization tools actually improve the quality of the generated images.
Okay, another practical plus they mentioned was flexibility with the step size, SAS in dollars. Why is EQM so much less sensitive to this compared to flow matching?
Right. This is a big deal for actually using these models. Flow matching relies on that time variable teller. The step size Ehlers is tied into how you discretize that continuous time pass. If you change it even a little bit, say from 0.004 to 0.005, you're fundamentally messing with the integration accuracy along that specific path. Quality can drop dramatically. But EQM is just trying to find the bottom of a static energy landscape. As long as your step size Eller is reasonable, not ridiculously large, so you overshoot gradient descent will eventually get you a minimum. They showed in the paper, I think it was figure 7, that EQM worked well across a much wider range of step sizes. The landscape seems really smooth and forgiving.
That must make tuning so much easier. Okay, let's talk efficiency. Adaptive compute. Saving up to 60% of function evaluations sounds amazing, but is there a risk? Do you potentially stop too early and hurt image quality?
That's the critical question, isn't it? How do you know when to stop? They handle this by setting a threshold based on the norm or the magnitude of the gradient. If the gradient magnitude drops below this threshold, it basically means the sample isn't being pushed strongly anymore. It's settled down into a flat region, likely a local minimum representing a good image.
So instead of just running for, say, 1,000 steps no matter what, you stop when the gradient tells you the image is basically done.
Exactly. It adapts. Some simple images might only need 200 steps to reach a low gradient norm. More complex ones might need 500. It adjusts dynamically. And the results show this saved, on average, about 60% of the function calls without hurting the final FID score. It confirms that for many samples, those last few hundred steps in a fixed step process were probably just wasted computation.
Good stuff. Let's touch on the theory quickly. What guarantees does the paper offer that EQM actually learns the right things, that the minima it creates correspond to real data?
Yeah, they provide some solid theoretical backing. Statement 1 basically says, if you train EQM perfectly, then the actual ground truth data points at Exagal will indeed have a near zero gradient. The model will recognize them as stable points. At X2 will be approximately 0. And statement 2 is kind of the crucial flip side. Almost any point where the gradient is 0, so very likely to be a point that looks like it came from the original data set. It gives you confidence that the minima you find during sampling are actually the images you want. They also show that the convergence of the gradient descent sampling process is bounded at O1K, which is typical for this kind of optimization, but good to formally confirm.
Okay, so solid theory and then the empirical results like that one on tiny EFID on ImageNet really drive it home.
It really does. I mean, comparing against the field, they didn't just edge out the competition. They set a new state-of-the-art against strong models like Stylogan XL, VDM+, Plus L, and especially Scite XL2, their main flow matching rival. And importantly, they showed it scales well. EQM consistently outperformed flow matching as they increased training time, model size S, B, L, XL parameters, and even patch size. It suggests this equilibrium approach might be fundamentally more robust as you throw more resources at it.
Okay, beyond just getting a better FID score, what about unique abilities? What can this equilibrium model do that's maybe harder or impossible for the traditional non-equilibrium time-dependent models?
Yeah, this is where the connection to energy-based models really shines. It gives you some neat multitask flexibility. Take partially noised image denoising, for instance. Flow-based models are often trained assuming you start from pure noise, time $2, and run the whole sequence back to $2. If you try to jump in halfway, say with an image that's only slightly noisy, they often break down because the velocity field they learned is optimized for that full trajectory.
Right, they expect to start at the beginning of the conveyor belt.
Exactly. But EQM isn't following a preset path. It's just rolling downhill on the energy landscape to find the nearest minimum. So you can give it a slightly noisy image, and it just starts descending from there. And interestingly, the paper shows its denoising quality actually gets better the less noise you start with. That's super useful for things like image editing or quick refinement.
That makes sense. What about other tasks, maybe more like classification? Can it tell if an image is weird or out of place?
Yeah, that's a classic EBM strength. Out of distribution, ODetection. EQM naturally assigns energy values. In distribution samples, the ones it was trained on, should have low energy. They're at the bottom of those energy values. ODE samples, things it's never seen before, tend to land on the high-energy hills or slopes between the valleys.
So high energy basically signals, warning, this doesn't look like anything I know.
Pretty much. They tested an explicit energy version, EQME, and found it got the best average AEROC score, 0.68, for ODetection, compared to several baselines like Pixel CNN++ and IGBM. So it's not just a good generator, it also learns a meaningful representation of the data's probability density.
Okay, one last cool feature. Compositionality. Combining concepts like generating a cat riding a bicycle is often really complex in diffusion models needing special techniques. How does EQM handle this?
This is another place where the energy landscape view makes things potentially much simpler. If you have two different EQM models, maybe one condition to generate panda images and another condition for valley images, each defines its own energy landscape. To generate an image with both concepts, you can simply add their gradients together at each step during sampling.
You just sum the forces from both landscapes.
Exactly. You're basically optimizing on a combined energy surface that tries to find points low in both the panda landscape and the valley landscape simultaneously. The paper showed some nice visual examples generating a panda and valley or even a car mirror and volcano just by adding the gradients from the respective conditional models. That kind of simple additive compositionality is really elegant and often hard to achieve cleanly in time-dependent frameworks.
Okay, let's circle back then, try to pull it all together. Equilibrium matching seems like it's offering this really powerful, maybe simpler, and definitely theoretically sound alternative. It neatly sidesteps the main complexities of non-equilibrium models.
I think that's right. We've seen that by sort of merging ideas from EBMs and flow models into this single equilibrium gradient, EQM not only gets state-of-the-art image quality, but also unlocks these more flexible and efficient inference methods, NAGD, adaptive steps, easy compositionality. That stability and the new possibilities it opens up feel like the key takeaways.
So given that EQM nails these top results without needing that explicit time or noise conditioning, it really poses a provocative question for the field, doesn't it? If this time-invariant energy landscape works so well, just how much extra baggage, how much unnecessary complexity have we maybe been carrying around in the standard time-dependent diffusion and flow frameworks all this time? If you're curious about the nuts and bolts and want to see how clean the implementation can be, you might want to check out the pseudocode in the paper itself. Algorithms 1 and 2 really lay out the core objective pretty clearly. It's surprisingly straightforward,